All right. Well, hi, everybody. It's been great hearing about some of the work going on so far in the conference. And so today in this presentation, we're going to be talking a little bit more about some of the social and interpersonal challenges that can arise in the context of collective intelligence, which is really just a big umbrella title for some actually really interesting and diverse projects. So in a moment, I'm going to turn it over to Iyad to talk about the first presentation. I just wanted to mention, if you would like to ask a question during the presentation, go ahead and put a note in the chat. If you want me to ask it for you because you can't, you're not in a place where you can turn your microphone on, go ahead and indicate that. Otherwise, I'll probably just use that as a prompt to call on you. Or you could raise your hand. I mean, I suppose we could do it either way, but I'll try to monitor both. But with that, without further ado, go ahead, Patty.
All right, thanks, Anita. Let me just share my screen and make sure the sound's on. So there are some interactive parts of this presentation, so put headphones on if you need it, because it was on audio. So thank you so much for having me today. This is some of the research that we're presenting. It's funded by the Defense Advanced Research Projects Agency, DARPA, and we're examining artificial social intelligence in teams. And so my research, my background is in emotions and decision-making, and I'm curious about a question about how emotions affect performance. And specifically, I'm interested in anger. So anger. There we go. Anger, does it help or hurt performance? On one hand, it could potentially be helpful. People that are angry tend to be goal-focused. They are oftentimes reward-oriented focused. They're much more persistent. And as we know, if people are persistent, they're more likely to achieve goals. So there's some evidence that participants expressing or feeling angry will use that as a boost in increasing performance. Now, on the other hand, anger could potentially be harmful in that you're oftentimes angry about something or someone. It's usually a reaction to a stimuli of some sort. And in some cases, you might be thinking about that norm violator, the person that made you feel angry. And so that's one feature of anger is rumination. You perseverate or you think about the norm violator themselves as you're experiencing the game or experiencing a task. So it's possible that anger can impair executive function because people are distracted because they're thinking about the transgressor. And so to give you a sense of how we tested this, we had this experimental procedure. We had participants play a search and rescue task across 3 rounds in a game that's developed in Minimap. And so we measured participants' emotions throughout the task, both before the game, between the rounds, as well as after the game. And at the end of the game, we also had some questions about participants' reactions to their teammates and their evaluations of the teammate. And so in the game itself, they met their teammate in the first round after doing some practice rounds. And the teammate was a reasonable teammate. They scored a reasonable amount of points. So they exerted a reasonable amount of effort, and they were relatively talkative to the teammate. In the second round, participants were either assigned to or not assigned to a condition that was intended to induce anger. And that's something that persisted in round 3 as well. So the anger inductions occurred in, or not occurred, in rounds 2 and 3. And then round 1 was used as a baseline skill measure. And so to give you a sense of the game itself, this is the game that was developed within Minimap. So from Nguyen, as well as Gonzalez from our own group, they developed this game. And it's basically, the game itself within Minimap is a search and rescue game where participants were tasked with going around the map space and looking for green and yellow box victims. And green box victims were lower value. They were available throughout the mission, throughout the entire mission, the 5-minute mission. And yellow box victims had higher value, but they expired within the mission. So in this case, they expired at 4 minutes. Participants were told they were matched with the teammate, and the teammate was that you were able to talk to the teammate through the chat function or the chat apparatus over to your right. And so they were able to talk to the teammate if they would like to and send messages back and forth. And so it's an important point here for the actual study itself and for the anger induction itself, is that participants were told that the number of points that they collectively earned with their teammates would determine a bonus above and beyond the regular pay rate that participants receive. So if both participants scored a reasonable amount of points, they would evenly split the bonus amongst the team members. I think that's everything. Yep. Okay, and so to give you a sense of what the anger condition looks like, take a look here. This is the video that we have. So what you see is a teammate that's social loafing. This is a clear sign of that. And participants oftentimes are expressing anger or outrage. They don't send the exact same message in the third round, but it's something similar. It's a social loafing reaction. So as far as the other measures of the game, we examined participants' emotions throughout the task before and after each of the rounds of the mini-map game. And we asked them using a pretty standard measure of how much they're expressing emotion by determining or indicating the degree of emotion they're experiencing on a scale from 0 to 100. And we used 2 items that were related to anger, angry and mad, and those were highly correlated to each other across all the different sets. And we also looked at mini-map performance, so things like the number of points they had scored, the degree of effort they exerted, so the number of steps they'd taken in the game, as well as the coverage, so the amount of space they covered relative to the entire map space. And something I should say that's important is that participants only were able to see that 5x5 window, that 5-block window of the space, so they couldn't see the entire space, so it was a relatively difficult game experience. And then we also measured rumination. And so in this case, we measured it in a couple of different ways. The first way we measured it was a post-task measure, where we asked participants a few questions about their teammate. And so some of those questions related to how much they thought about their teammate. And so here's one question that we asked that was related to thinking about or perseverating about their teammate. We also measured rumination using an in-game measure. And in this case, we thought the degree of messaging that is sent, both in terms of frequency as well as length, so the number of characters that are sent, could be a reasonable measure of rumination. And so that's what we used there as well. And those were correlated with one another. The in-game messaging was correlated with the post-task measure. And so the question is, does anger affect performance? But the first question is, was our induction successful in manipulating anger? And so we can say, I think pretty definitively, the answer is yes. Participants in the post-induction participants expressed much higher levels of anger relative to those participants in the control condition, as you see on the right part of this graph. Participants in this anger condition did express greater levels of anger. And importantly, we're also finding differences before and after the intervention, and that was only relevant for the anger condition. Participants express much higher levels of anger within subjects after the induction relative to before the induction. So our next question, now that we've manipulated what we intended to manipulate, we wondered whether or not anger had an effect on performance. And so what we find is evidence for the latter, that anger is harmful. Participants scored fewer points as a result of being assigned to the anger condition. And all of these effects that I'll be presenting in a second, or that I'm presenting now, control for that baseline skill. So we're looking at just their performance in rounds 2 and 3, and collapsed rounds 2 and 3 because they're essentially identical to one another. But what we find is that the anger condition reduced the number of points scored, reduced the amount of effort that's exerted. It reduced the amount of coverage that participants had covered in the game if they were randomly assigned to this anger reduction condition. But we're also finding, because people are playing this game multiple times, and it's an identical map each time, that we wondered, does it actually affect participants' learning? And we're finding that to be the case. Generally speaking, participants in this control condition did improve their performance as they play the game more and more. So in round one, they did a reasonable job. They got about 170 points. But in the second and third rounds of that combined measure, they scored over 60 or 70 points higher than what they had scored. And so we are finding some pretty good evidence that, generally speaking, people learn the map, learn where all the victims are, and save the victims. The same can be said for the anger induction, where we did not find a significant effect. One that was close, of course, but not statistically significant. Really, what I would point out here is the magnitude of differences in effect size, where the controlled conditions effect size before and after the induction was approximately 5 times larger than that from the anger condition. And so one explanatory mechanism for these effects could be rumination. Did participants think about their teammate more often in the anger condition? The answer is yes. They were more likely to report greater thoughts about their teammate. They would respond with higher numbers based on this Likert scale relative to those participants in the control. So in this post-task measure of rumination, we do find evidence that participants are ruminating about their teammate relative to control that's much higher in the anger condition. What we're also finding is that participants are writing longer messages to their teammate, as well as more frequent messages to their teammate if they were assigned to the anger condition relative to control. So we find pretty consistent evidence of rumination here, regardless of whether or not we're using these post-task measures or tasks that are within the context themselves. And another thing I'll note, I haven't presented it here, we are finding some evidence of deviation as well. Participants that were assigned to this anger condition did ruminate more, and as a result of ruminating more, they covered less space. And so we at least have some evidence of rumination that's occurring, that's causing the drop in performance. So in summary, anger does harm performance. People that are angry in a team-based context showed reduced levels of performance, whether that be them against themselves in a previous match or a previous round, or against teammates that were not induced to experience anger. And one potential mechanism is rumination, and that's one that we'll be digging a little more into as we further on our research agenda. So for future research, we're looking at going in a number of different ways. One of those is the use of artificial intelligence to help give people that are angry advice using AI, whether it be anger at Siri for not listening or Alexa for not listening to them correctly, or for, being angry about Google Maps taking you down the wrong direction or wrong pathway. And those, and in the context of this game itself, or this game that was developed in Minimap, those could be things like increasing effort, using interventions to increase effort or coverage, the amount of space that's being covered, or ways to limit or reduce rumination as a result of experiencing anger. We next wondered whether anger has an effect on collaboration. And we wondered, in a team-based context, do people that are experiencing anger, does that affect the degree of being a reasonable or good teammate? And whether that be interdependent sort of behavior, helping behavior, or other sorts of tasks, does feeling anger affect collaboration? Third, does the source of anger have an effect on both individual performance, team performance, or collaboration? That's a third question that we're looking at asking. We do have some evidence in a different study from a game that was developed in Minecraft. And in that case, we had participants write about an event that made them feel angry in their personal life, and then they played a game of Minecraft. We do have at least some evidence that that condition also affected performance relative to a control condition in terms of the number of points they accumulated and the amount of coverage they had in the game. And then finally, does individual or collective anger that's experienced in a team-based task, does that have an effect on collective intelligence? So those are some of the pathways that we look at sort of furthering as we further our research agenda. But that's all the stuff that I have for you today. So thank you so much for listening, and I'm happy to take questions.
Thanks, Fatty. Well, we're actually, I think, kind of at time, but in the chat here, I've put the link to where there's additional discussion for the paper on LinkedIn. So if folks have questions, go ahead and you can head over there. And if we have some time at the end, we can take some additional questions. So why don't we go ahead and move on to our second paper. I believe Nguyen is going to be presenting that. So Ngoc, if you want to take over the screen, you can go ahead.
Yes. Okay, thank you. Let me share my screen.
I think, do you have the share screen button showing?
Yeah, let me share my screen.
Yeah, great.
Okay, hello everyone. Welcome to our talk title, A Cognitive Hysteretic-IBL Model for Coordinated Multi-Agent Transportation Problems. This is the joint work with my colleagues, Nhat, Phan, and Gonzalez. So in this talk, we start with the introduction of Coordinated Multi-Agent Object Transportation Problem, CMOTP. And then we continue with the explanation of Hysteretic-IBL model. We end with the experiment designs and some findings that we learned from the experiment. So to get the general idea of the coordination task, we look at the taxonomy of a multi-agent system based on the type of task. So according to the taxonomy, there are three main settings: competitive, cooperative, and mixed setting. And the coordination task is classified as fully cooperative. That is, it is referred to the ability of the multi-agents to jointly reach an agreement on which actions to perform within a shared environment. The applications of the coordination task can be found in various settings. For instance, a group of bots might be required to coordinate to pick up, carry, and deliver items, which is referred to a coordination object transportation. So this is the CMOTP task simulated in the real-world environment. So to accomplish the task, two agents, as you see here, must exit the room one by one to locate and pick up the item G. So the pickup is only possible when the agents stand on the left and the right-hand side of the item, as you see in this figure. Then after the pickup, the agents, the item can only be transported or carried when the agent successfully grabs the item by always being side by side of the item and decide to move in the same direction. So this is the animated demonstration of the task. As you can see that the green agent successfully found the item first, but it has to wait for the red agent to pick the item up. So then they are now in an attempt to carry that item to put into one of their two drop zones. And the items only receive the positive reward if they successfully place the item into one of the two drop zones. So there are several challenges presenting to the items, presenting to the agents in this type of task. So the first one is the simultaneous learning to coordinate. That is, if the agents selects what appears to be an optimal action for itself as an individual, it could end up with poor joint actions as a teammate, which refer to a miscoordination. So then the stochasticity in the reward also adds a further complication to the task. In particular, there are two drop zones. The first drop zone is deterministic, which returns the reward of 0.8 all the time. But the drop zone 2 is stochastic. That is, it's returned the reward of 1 60% of time, but the reward of 0.4 40% of time. And the last challenge here is that there's no communication among the agents. So they are called independent learner or non-communicative agents. So the agent cannot observe the reward or the actions taken by each other. So in the literature, various reinforcement learning algorithms have been proposed to solving these challenges in the CMOTP task. One of the prominent and recent approach is the integration of hysteretic Q-learning into multi-agent deep reinforcement learning. So despite the advance in deep reinforcement learning research, we also observe that they are still unclear how do agents could coordinate with human in this type of task, knowing that the research in cognitive science suggests that the model that can successfully or accurately represent human behavior could collaborate with humans more successfully than the models just focus on the engineer aspects. And also we want to investigate if the model that is based on the cognitive aspect of learning can do the task better than state-of-the-art algorithms. So that's why we've come up with the Hysteretic-IBL model. In essence, it's a combination of IBL model and the hysteretic idea in reinforcement learning. So the IBL model is based on the instance-based learning theory, and it is a theoretical grounded in human cognition with the proven ability to explain human making decisions from experience. So it leverages the cognitive mechanism of memory, recency, frequency biases, and pattern matching using the blending value. So regarding the hysteretic idea in reinforcement learning, it's based on the optimistic learning idea. So in an intuitive way of explaining this idea is that the agent will select any action that it finds suitable with the expectation that the other agents also choose the best match accordingly. So under this assumption, the agent will always prefer the superior results. So here is the generic model of the cognitive idea model. So the instance here is the memory unit, which is represented by the tuple observation O, action A, and outcome X. So in this type of task, an observation O takes form of X, Y, and H, where X, Y is agent's location and H is the status of the pickup. The action is one of the action from the set moving up, down, left, right, or choose to stay in place. So according to the model, the agent will always select the action that has the highest blending value. And then it takes the action, move to a new state, new observation, and get the outcome. But more importantly, in this type of task, the feedback is delayed, which is that the agents can only observe the real outcome after the end of the task. So we use the temporal difference error to estimate the outcome of every decision making after every step. And here's the full procedural form of Hysteretic-IBL. So this slide, number 5, you can see that the model used the decreasing epsilon greedy exploration strategy to have the exploration exploitation trade-off. And this slide shows how to compute the temporal difference based on the blending value of the IBL model. And this slide number 8 here is the implementation of the hysteretic idea in reinforcement learning. So because the agents always prefers the superior results, so it uses 2 learning grades to update the results. So regarding the experiment, we consider the stochastic CMOTP task within a 12 by 12 grid world. We compare our hysteretic IBL model against the hysteretic deep Q network, and we perform 20 runnings of 500 episodes per running. An episode ends when 2500 step limit is reached, or when the agent successfully place the item inside one of the 2 drop zones. So regarding the dependent variables, we measure the average number of steps and the average reward. So here are the results. As you can see that the Hysteretic-IBL model, represented by the red line here, learns much faster. It converges to an optimal job policy faster just within the first 100 episodes. But the deep reinforcement, hysteretic deep reinforcement learning would take a longer to get that performance. And the Hysteretic-IBL model also attain a higher expected reward sooner than the other area. So to conclude, in this work, we have demonstrated the advantage of combining our computational and the cognitive approaches or in the CMOTB task over the state-of-the-art algorithm. So in future work, we can use the Hysteretic-IBL model to support or improve the human performance, given that our model is based on the cognitive modeling. And we also expect that with that, the Hysteretic-IBL model could be an effective human teammate in the human-machine team task. But we leave that for the future work. So thank you very much for your attention. I'm happy to answer the questions.
Great, thanks, Ngoc. We do have a few minutes if people do have questions now for Ngoc. You can go ahead and raise your hand or put them in the chat. Otherwise, we can also move on and we'll have some time at the end for questions. So I'm not seeing any hands, so maybe we'll go ahead and move on. Also, here is the link if you want to discuss the paper on the discussion board online as well. So let us move on now, I guess, to paper 3, and that's going to be presented by Stephen McCarthy. So Stephen.
Yep, thanks, Anita. Just share my screen. Great, yeah. So firstly, thanks very much for the opportunity to speak today. My name is Stephen McCarthy. I'm from University College Cork in Ireland. And today I'm going to speak about our extended abstract, which is I'll be watching you, a social cognitive theory perspective of his relationship with surveillance capitalism. So to begin just by providing an overview of this term, surveillance capitalism, some of you may already be aware. It comes from the work of Shoshana Zuboff, a Harvard professor, who speaks about this new economic model, which is primarily based on the logic of accumulation, where as much data is gathered online as possible for the purposes of monetization. And primarily what we're talking about here is personal data. The output then is to create predictive products, which will building on the data, identify patterns, and ultimately try and shape behaviors towards some desired outcome. So these practices vary in terms of controversy. In the far left, the least controversial would be recommendation engines, say on e-commerce platforms, which are primarily about trying to showcase products available, which might be of interest to the customer. More controversial than something like Pokemon Go, which has had a lot of privacy questions raised, the tracking of user data over time, as well as retailers' use of the platform to bring users towards their store. Again, not very controversial, but going to the far end of the spectrum where we see the use of facial recognition technologies, trying to anticipate human emotions and ultimately then provoke some kind of behavior also through that. So on social media, we also see examples of Cambridge Analytica, the common one we've all had where we search something online and then for the next few weeks we see a certain type of advert come up continuously for us. So this can create a sense of an invasion of privacy, in particular because the secrecy around some of the data analytic practices behind them, which is by intention. So it's intended to be undetectable as far as possible for the user. based on this question of ethics, a lot of academics have called for increased citizen engagement in this area, particularly as citizens, their data is the product of surveillance capitalism. So the likes of Google and Facebook, the product is the data, and the auction is of the data and the ability to use these predictive products for advertisers and other third parties. So citizen engagement is based on this notion that we try and bring together as many perspectives as possible to get a more complete view of the topic of interest. So very much in keeping with this idea of collective intelligence. For instance, the work of Mirza Walsham, this idea of discourse ethics, which builds on previous work by Jürgen Habermas and theory of communicative action, the idea that people's own life world reasoning or everyday lived experience has weight, and while it's a starting point, it needs to be exposed to criticism, and then we get a better understanding of how we can take moral actions to try and create a more just and democratic approach. So our study is one of citizen engagement. It's primarily qualitative in that we brought together groups of citizens for a dedicated amount of time online because of the pandemic, and try and hear their views, firstly on their awareness of surveillance capitalism, and then their perspectives and feelings about that, as well as then some of the actions they feel they are empowered to take to protect their privacy. To provide us with a better understanding of citizens' perspectives in relation to surveillance capitalism, we have initially drawn on some concepts from social cognitive theory. Obviously, social cognitive theory is a much broader theoretical framework, but three concepts in particular we're looking at based on our interest in particularly human agency. So moving beyond this idea of deterministic forces that people are completely at the whim of big tech, to see how citizens feel that they, firstly, are relating to these practices, which again are shrouded in secrecy and potentially undetectable, moving to the evaluation and eventually the control citizens feel they have. So social cognitive theory, based on the work of Bandura, it looks at the interplay between the environment, interpersonal influences, and then the individual behaviors. So particularly when it comes to human agency, the concept of self-reactiveness, the ability, for instance, of a citizen to detect when some of these practices are being used, when their data is firstly being analyzed and then some predictive product is being used to then target something towards them, usually with some experiment in mind. Self-reflectiveness, then the judgment, the evaluation of that experience or observation in terms of the citizen's values and meanings of pursuit. And finally, self-efficacy, based on these prior stages, how confident does a citizen feel that they can do something about it? How much control do they feel they have to adjust the data that's being, the personal data that's being taken and used, as well as refining it and again, just giving feedback towards that. So in terms of the conceptual diagram, again, trying to figure out this broad notion of surveillance capitalism, it's still quite, I guess, uncertain, the meanings, and Zuboff's work, while it goes back many years, the concept more recently emerged as part of a Journal of IT article and more recently a book that she's published. So it's quite emergent in terms of theoretical perspectives, but trying to, again, bring the citizen into this conversation, because of their role, and again, this idea of the citizen as a product, so to speak. So when the citizen is being involved in experimentation based on their personal data, democratically, it makes sense to involve them and allow them to have their say. So the case study description then, so back in October, we ran a series of citizen consultations, which as I mentioned, were done online because of the pandemic. So it was quite a ambitious undertaking. It was run by Mission Publique in France, who coordinated consultations across most continents of the world. So it involved countries from North America, South America, Africa, Australia, Asia. In Ireland, Cork University Business School ran a consultation with about 30 citizens, and took place over 2 days, totaling about 16 hours between breakout rooms, which were running simultaneously. And the aim was to try and build recommendations for policymakers. So it had strategic partnerships with the likes of the United Nations, European Commission, as well as the private sector, such as Google, with Vince Jeff also contributing and furthering the recommendations that came out. So it was broadly focused on the internet governance, but within the themes, we specifically looked at things around data analytics, and what I've previously spoke about surveillance capitalism, as well as more broadly issues such as fake news, digital identity, and so forth. Again, allowing citizens to bring forward their perspectives. So I'll just focus on a snapshot of results from the Irish dialogue. We had some surveys as well, which we were using to kind of compare before the dialogue to after the dialogue, in terms of how people's perspectives might have changed. But up front, it was quite obvious people generally had, firstly, a sense of distrust to how their data is being collected and used when it comes to both private companies as well as government organizations, but more so that trust, that lack of trust being based on a lack of awareness of what's actually being done with the data. So they expressing a certain amount of general uncertainty around what data is being gathered, who's using that data, how it's stored, and generally the pipeline of what's then done with the data. This broadly speaks to platforms such as social media, more broadly to public platforms, but just trying to hear citizens' views and understanding of their personal data online. And some sample quotes. So as I say, primarily just focus on the qualitative nature of the results. There was a lot of personal accounts of, again, something we've all probably experienced, but the notion that you search for, say, garden sheds, and over the next 3 weeks you see garden sheds, and a general suspicion of phones listening, even while passively, by the citizen side. So equally, the awareness of certain amount of cautions for vulnerable groups when it comes to younger users who firstly may not fully understand the idea of privacy online and are generally maybe more active when it comes to producing that data. And then finally, the concern around what to do. So a lot of discussion around the legalese used in terms and conditions. For instance, personal assistants like Nest thermostats, there being hundreds of embedded contracts that essentially you have to accept to use the product. The risk of not accepting it ends up creating issues such as frozen pipes and other unintended consequences if you're not going to buy in. So then building in social cognitive theory, interestingly, we did find, although a lot of these practices are by design intended to be undetectable, citizens are aware of what's going on in the background, and a certain apprehension as well of what happens. and broad context of use, be it from insurance companies to political organizations, or generally just targeted display advertising. In terms of self-reflection, citizens also were quite honest in that they did recognize a trade-off and felt more accepting of these practices when it came to entertainment companies. So when it comes to the likes of Netflix or Spotify, the convenience of having recommendations which were going to be delivered to them, and certain trust in those platforms, versus social media, increasing level of distrust, what could be done with the data, and what kind of content and experimentation could be done with their engagement. And as I mentioned, and similarly in terms of the control that citizens feel they have, information overload being of key concern, and again, something we're all probably guilty of, the automatic accept of terms and conditions to use apps. And again, Shoshana Zuboff speaks to this idea of the effect of life, that nowadays we are automatically accepting this because these apps and platforms, we rely on them as far as socializing, as far as work, many other contexts of use. So the idea of bringing citizens in here is that we can stimulate discussion about that and try and again encourage a certain amount of recognition of issues, as well as trying to create a more democratic result for everyone, essentially. It's not trying to shut down these uses of technology, but rather create more ethical and responsible use of them for everyone concerned. So we're kind of in the early stages. As I say, the data was kind of gathered just in the early part of October, and we started pulling out some results, qualitative results from 16 hours of dialogue. As part of this project as well, dissemination efforts have been ongoing. So the results have been fed back to the United Nations, as well as Google, and the results were also published at a project level at the Internet Governance Forum last November. But we really welcome any feedback, as I say, because this is something that we're hoping to engage a bit further with and build out a bit more. So if anyone has any feedback or any questions, I'm happy to take them. And equally, my email address is there if anyone wants to get in touch about any avenues of research around this. So yeah, thanks very much for your attention.
Great. Thank you very much, Stephen. And I guess in keeping with what our pattern has become in this session, I'll just invite everybody to go ahead to the online discussion. If you have questions, if you have tried to access that and haven't been able to, it might be that you need to join the LinkedIn group. So I've put that link in the chat. So go to that first and ask for permission, and our kind organizers will grant you access with the powers that they have to do so. And then here I'll paste in specifically the link for Stephen and his collaborators' paper. These are all linked in the program as well, if you are looking for them later. All right, well then, last but not least, let me turn the floor over for our final paper, and I believe that will be presented by, Levin Brinkmann. Yes, yeah. Sorry. I just wanted to make sure that I was remembering that right. Thanks very much. So go ahead and take over the screen and get us started.
Yeah, thanks a lot. I'm super excited to talk about this work I did together with Deniz, Gezerli, Kleist, Thomas Müller, Iyad, and Nicolo Pescatelli. And what I would like to talk about is human biases in cultural transmission between humans and algorithms. But before I actually show some experimental results, I would like to give you a bit of an idea about where this inspiration came from for this work. So we were quite excited about this event in 2016 when AlphaGo was beating Lise et al. And back then, commenters were really pointing out the specific move 37 in game 3. And they said that was a very unconventional move and that no human would have done such a move. And just in the next year, in 2017, AlphaGo 0 was released. And what's special there is that's an algorithm which was trained just without any human input, just trained by self-play. So that brings us into the situation that we have two cultures of Go play. So on one hand side, of course, the human culture of Go play, but also we have an artificial culture, like new culture of Go playing from this Go play from this algorithm. And then the natural question also, of course, arises, like, is this actually influenced the human culture of Go play? And that was answered by Chin, Kim, and Kim. And what they found was that in 2017, when an open source version of AlphaGo 0 was released, precisely in that moment, the gameplay of humans converged to in some way towards the gameplay of the algorithm. So now we know that like a superhuman algorithm can influence human behavior. But we thought a bit orthogonal to that. So what we also know is that, or like what there's this kind of idea that more diverse groups are like a source for greater innovation and more culture evolution, like increasing cultural evolution. So that kind of raises the question when we now move from like a human collective to a hybrid collective where we have humans and algorithms. Maybe we have an increasing cognitive diversity, and we might also see leapfrogging innovation. And so what we really want to look at is kind of the interaction of human and alien algorithmic cognition. So the way we think about that is that humans use heuristics as effective adaptation to the environment, but we also know that these heuristics can be misadaptive. And then what, on the other hand, AI is still very specialized nowadays. So it's kind of easy to imagine that AI might be just like designed or trained very specifically to specific environments. And these specific environments, they might be well suited in complementing human biases and heuristics. So that kind of leads us to the question, like, can humans then benefit from these alien algorithmic solutions via social learning? But we also wanted to take the perspective of cultural evolution. And what we actually wanted to additionally ask is, like, once we have this transmission from the algorithm to the human, are these alien solutions then further transmitted between humans via social learning? And for these reasons, in our experiment, we compared two chains, a chain of humans only and a hybrid chain where we put an algorithm in generation 2, and yeah, compared the performance of those two. Now, this is a lab, like an online lab experiment. So we wanted to have a task, like a simple task, where we know there is a specific human bias. And so we utilized this network task from Ruiz et al. And the good thing there was for us was, so the task is actually to just like find the path of 8 steps, which is maximizing your reward, starting in this case from node E. But what we know is that there's a strong human bias on this task. So humans tend to, when they like search for different options, different possible paths, they don't really consider those paths which start or like have in like an early step a large loss. And they don't even consider those paths when later on in the future there might be like a bigger gain which would compensate this large loss at the beginning. And so we call this this bias like the aversive pruning bias, which was found by Quentin networks. So, and they also formulated this mathematical model to describe human behavior. And on pilot data, we just could represent their results. So what we found, like this specific pruning was much higher than the general pruning and specific pruning after these large losses. So that means humans less consider a path with large losses, and then we just tuned an algorithm to behave the opposite. So this algorithm would more likely consider paths with large losses. So this is how the experiment kind of looked in practice. First, people would be seeing the previous player in the chain playing on a specific network. Then they were playing themselves, entering the solution, and then they were getting the feedback about how well they performed. Now, we had a 2x2 design. So on the one hand side, we had the two chains, as explained earlier, but also we had two different environment types. So we classified these networks, we randomly generated them, and then we classified them in either networks where we know that human biases would fit well the network. So we expected humans to perform good. And on the other hand, we had networks where it was the opposite. So humans were expecting to perform bad, but the algorithm in inverse was expected to perform good. And this last case is the one where we are specifically excited about. Now, just as a first validation that the whole setup kind of worked, we looked into the human-only chains, and what we saw there was that there, when we looked in individual chains, there was an improvement of performance over the 8th generation. So some kind of, there is like some kind of social learning or cultural transmission happening. Otherwise, we wouldn't see that improvement. But then we look, of course, into the difference. So, like the question was really, how do these two chains compare? And what we first of all see that indeed, like in generation 2, the algorithm is having a higher performance than the human participants, and specifically in this human forgetful case, the algorithm has this higher performance. And what we also see that in the generations as following, so in the 3rd generation, there's still a higher performance from the human. But then this effect quickly levels out, and what we see in later generation is that there's no difference between the two chains. Now, that was just the performance, but we also looked into like how the quality of the solution, and there we fitted the model which I described before onto each individual generation and condition. And we're specifically looking at this gamma specific, this pruning of after large losses. And again, we see like our algorithm by design is pruning much less after large losses, but and we can still see this effect in the generation following the algorithm in the generation 2 in humans. But then later on, there's no difference between the two conditions. So obviously we ask now the question, why? Like these algorithmic solutions are better in performance, but still they are not kept in doing this transmission chain experiment. And maybe the boring answer is that in generally there was a lot of loss, like transmission, like errors in transmission. So the similarity of the solutions now from solution 2 to the following generation, from generation 2 to the following generations, that similarity decayed very quickly. But there's also a little bit more exciting answer to that. And this more exciting answer is that when we specifically looked into like these copy errors, and now we look first into the copy errors from generation 2 to generation 3. So in generation 2, we have the machine in the hybrid case. And what we see here is that as expected, solutions with higher rewards are copied more. But what we also see is that solutions from the algorithm are copied less. So now I think you lost the slides. And I don't know why. I hope they are back. Are the slides back?
Yeah, we can see the slides.
All right. Okay. Sorry, my screen was suddenly like. Okay. Sorry about that. So trying to jump in again. So what I just said is that we had like we saw that solutions from the algorithm was copied less. And now it's very important to note that we didn't disclose to the participants whether the previous solution was from the algorithm or not. So in social learning, there are two different types of biases. One is about like the features of the person you're copying your model, and that's context bias, but we can rule out that because there was no difference between the two conditions. So what we really looking at here is content bias. So in some way, the solution themselves were somehow less liked by the humans. And we look more precisely into that when we just focus on the human-only chains. And what we saw there is, again, solutions with higher rewards were copied more, but also solutions with fewer large costs were copied more. So kind of a confirmation of that result. So just to kind of like wrap up, we kind of make a replication of these results with an agent-based model. And we had, importantly, like, first of all, you see that like blue and orange are the two conditions as an experiment. And like, if you just go to time in like generation infinity, like always everyone is converging at some point because there is some kind of loss between the generations. But more excitingly is we had two different types of agents. On the one hand side, agents which just copied utilitarian just based on the reward of the previous solution, but other agents which also considered whether their solution they want to copy also fits their own bias. And what we see is when in this latter case that this convergence is much quicker and actually very similar to our experimental results. Just after 2 generations, there's almost no difference between the 2 conditions. So as a takeaway, there might be a lot of ethical concerns when we think about using algorithms to influence collective behavior, and that's a totally different story. But nevertheless, even if we try to do so, I think it's reasonable to do, then what we might be seeing is that content bias of humans might kind of put a barrier or limit to this, and so that we will not necessarily be successful, that humans would be able to learn from specialized algorithm. And second, what we kind of learned is that this content bias would then also could lead to a situation that like a new alien solution entered into human culture would not be able to preserve over like further transmissions. So it's important to note really that in this study, there are a lot of limitations. We put participants on a very high cognitive load. They had only few, like 15 seconds kind of to enter their solution. They only had 1 model to learn from. So that's also maybe a reason why we had large loss. And there was no repeated interaction with the same environment. But now without further ado, I would like to thank my collaborators on this work. We also have a preprint out, so have a look on that. And maybe there are some questions now, or otherwise I'm happy also to answer them later on in the chat.
Thank you. Thank you very much. Well, we do have a few minutes. If people do have questions for Levin or any of the authors, go ahead and you can put them in the chat. Since I don't see any yet, I actually might cold call Ben Town because he's doing something that I love it when my students do, which is make a connection between something in this session and something in a prior session. And so he put a comment in the chat. Ben, I don't know if you want to say a few words about your observation there?
Yeah, well, the study yesterday was looking at Twitter bots and how they might interact with a small number of users, but that impact can then propagate through. And here it's almost like an opposite finding. And I think that one of the reasons might be that it was hard for people to understand or receive the message from the algorithm about this being a better way, and hard for them to like mentally grasp that concept of the alternative path. There wasn't really a language that people have internally that's easy to use to describe that. And I think that that may have had something to do with why it was harder to learn or transmit, and why somewhat opposite result might have been found in that Twitter bot study, even though that was also
absolutely. I mean, that's kind of what the way of thinking we have, that we put people on a very high cognitive load, and if they cannot kind of fit this solution to their own model they have just present in that moment, then they will just not be able to reproduce their these solutions. But we're also thinking about whether that's might be different if we are in a different situation where maybe the algorithm explains also why it's kind of thinking that this solution is superior to another solution, and that would be just one way of going forward.
I also kind of wonder what would happen if you change the metaphor. So instead of being like a network with numbers that's a little harder to conceptualize, if you made it like a topography, and people are going over hills or something to get to a particular destination, and you give it more real world constraints, particularly if you recruit people who are in an environment where they have to solve that frequently. So if you're going with the topography example, you might have more luck recruiting in, say, Pittsburgh than in Kansas State or something.
Okay, sounds interesting. Yeah, we were considering that is a kind of wildcat well problem, I think.
Great. All right. Well, these sessions always go by so quickly, so it looks like we're actually about at our time here. But here, so is the link if you want to follow up on the fourth paper with questions in the online discussion. There's a link there, and scroll up if you need to get access to the groups on LinkedIn first, so that you can actually see the posts and make posts. But I want to just thank all of our presenters for giving us a quick overview of your work, and yeah, look forward to ongoing discussions. Thanks, everyone.